This question turns out has one of the hardest questions in the exam for this exam, question 6C, but we'll go through A and B first and move on to C. This is a spring and got a 1 kg mass on it, and they've given us the spring constant, the K there. So normal length is 2 meters. They hang the mass on and it stretches by itself to 1 meter, and in this case they pull it down to here and let it go, and it bounces up and down and up and down and up and down. Before we even go into answering the question, let's just think about what sort of energy there is in this sort of question. It's going to be helpful. As it bounces up and down and up and down and up and down, at the top it has the spring potential energy is 0 as it's unstretched. Down the bottom the spring potential energy is lots. In the middle the spring potential energy is something as well. At the top the gravitational potential energy is lots. At the bottom the gravitational potential energy is 0, and in the middle gravitational potential energy equals something. And at the top the kinetic energy is 0 because it's up, slows down, stops, and then comes back down. At the bottom the kinetic energy is 0, and in the middle somewhere, as it's moving through here, the kinetic energy is something as well. We don't know what that is yet, so just thinking about what types of energy there is at each of the places. I've called the 0 potential energy, gravitational potential energy is at the bottom. Yeah, that makes sense. Alright, so this is the graph of the same thing. At the bottom there's no gravitational potential energy, that's what we said, and at the top there's maximum gravitational potential energy. At the bottom the spring's stretched the most because it's got the most stretchy energy. At the top it's not stretched at all, so there's a 0 there. They haven't shown you kinetic energy on this. Calculate the total energy of the system when the mass is at its lowest point, Z. So when it's at Z, it's got gravitational potential energy equals 0. Even though it's not on here, we know at the bottom point the kinetic energy, because it's not moving, is also equal to 0. And the spring potential energy equals 20. So 0 plus 0 plus 20 equals 20 joules. Um, 6B. Right, same question again, same graph. From the data, calculate the speed of the mass at its midpoint y. Its speed here. So we know from the last one that the total energy in the system won't change, and it's always going to be 20 joules, what we calculated. You can't just grab energy from somewhere else or make its own energy. The energy is converted between spring potential, gravitational potential, and kinetic. And at y, in the middle there, we've got, according to this graph, the gravitational potential energy is here, it's 10. We've got the spring potential energy is this guy here, it's 5. Therefore, 20 minus 10 minus 5 equals 5. So the kinetic energy equals 5 joules. And I've just started numbering because it just helps me, helps you follow clearly what's going on with my working. It's not necessarily what the marks are given out for, but a lot of the cases it's pretty close. This is, I'm going to have 3 steps of working, but it's only worth 2 marks. Anyway, I've got my kinetic energy, and we know kinetic energy equals half mv squared, and I want to find the speed, so I'm going to rearrange to find v. So 5 equals half mv squared, so I'm going to put 2 on both, 2 times 5 divided by m equals v squared, which equals 10 divided by, what's the mass of this thing? Mass is 1. 10 divided by 1 equals v squared, so v equals the square root of 10, which equals 3.2. Alright, now this last question, this 6C, which was the hardest question, I think. from memory, only 6% of people got full marks on this question. It was a very tough question. Alright, now the students, here's the unstretched length. They now pull it down a bit further. Only 0.5 down instead of the 1 metre down, and oscillates back and forth like that. The students take the 0 to be here, so this is gravitational potential energy equals 0. That's what they're going to say is 0, so it has a higher one up there. And they've done some calculations. They've also taken the 0 of the spring potential energy to be here. So the students say spring potential energy equals 0 at this point when it's here. And they prepare their following table. So they say at Q and at P. At Q we've got 1 10 joules and 0 joules and 0 joules equals a total of 10 joules. And down the bottom they've got 0 plus 5 plus 0 equals a total of 5 joules. How are these different? This is what they're looking at. 10 joules is different from their calculation of 5 joules. What the heck? So we had to explain the mistake the students had made. And this isn't something you can, well, I mean it is something you could probably figure out if you had enough time. But certainly from practicing and seeing this as you're seeing it now, it's going to make it a lot easier to understand how springs work, and if anything like this came up in the future. Alright, the mistake they made for the first dot point for 3 marks here is that you can't, what they've done is they've taken, it's this thing here, the 0 of the spring potential energy to be at Q. That's the mistake. They said this spring potential energy here is 0 and here it's more stretched. The spring potential energy is 0 at this point here. That's the mistake they made, and now I'm just going to write about it to get my full marks and show you why that's the case. So let's write it. You can't take spring potential energy equals 0 at Q. You must take spring potential energy equals 0 at unstretched really, which is 2 meters. Okay. So if we did the proper calculation with it, taking the spring potential energy at 2 meters, we have at Q, so Q is here, which Q is the top here. Q is 0.5 stretch. So at Q we have spring potential energy equals half K change in X squared, which equals half, same K, so times 10 and times 0.5 squared, that equals 1.25 joules. And then if you do the calculation at P, the spring potential energy equals a half times K times change in X squared, and at P, which is down here, it's stretched by 1.5 meters. Is it really meters? It is meters. It's a long spring. Half times 10 times 1.5 squared, and that equals 11.25 joules. My last dot point to show the total energies. So at Q, total equals same 10 joules plus 1.25 joules, because this has now become 1.25, calculated here, and that equals 11.25 joules. And at P, the total energy now equals 0 plus my new spring 11.25 joules equals 11.25 joules. So now they're the same. So I'll fix the problem. Just to sum that up again, it's a very, very difficult question. But in terms of gravitational potential energy, you can pick anywhere to be the gravitational potential energy 0. Okay, you could have picked this to be the gravitational potential energy 0, and then done your calculations from there and said this is 0.5 meters above it and this one is 1.5 meters above it. That's fine. The reason you can do that is gravitational potential energy is linear. The calculation is linear, and so it works to pick it wherever you want. Because this calculation is quadratic, you've got the square in here, you can't pick it to be wherever you want. You have to always pick it where it's unstretched. So this is always the starting point where the change in x is 0 at the unstretched length, because it's this quadratic. If you pick it somewhere else, then it mucks it up, as these people have done, and it gives you strange answers. So that's the answer, and the way I wrote about it, I said it here, and then I wrote about it by just actually doing the proper calculations and giving the answers and showing that it works out.